Today's notes for 7.2 are going to take us to some other parts of your identity sheet. Particularly, we're going to focus on addition-subtraction formulas or addition-subtraction identities. So you might as well get your identity sheet out if you don't have it out already. And that area of the identity sheet, or what those identities are for, is to evaluate angles that are not common angles. The common angles we would consider to be the angles from the unit circle that are multiples of 30, 60, and 45, or pi over 6, pi over 3, and pi over 4. So an angle that's not common would be something like 15, 105, 5 pi over 12. But how we use the sum and difference identities or formulas is to create a pair of angles that, whether you add or subtract, would give you the angle that you're looking for. So, for example, let's say I said, let's find the sine of 15 degrees. Well, 15 degrees is not an angle off the unit circle, not a common angle. But I can say 15 is the same as 45 minus 30. Well, 45 and 30 are common angles. So based on that, I can then use the 45 and the 30 and expand it out with the identity, and then go to my unit circle to answer the question. So basically, the unit circle is definitely going to come back in these problems. The biggest thing, if there is anything about this particular kind of problem, is just that, can you create the pair? Creating the pair with degrees is pretty easy. Creating the pair with pi measure, actually, at first might not seem that easy, but I'll show you guys a simple way to go through that. So let me give you some examples of what are non-common angles and how we can create those pairs. We're going to start with degrees. So, for example, 75, 105, 165, 15, 105. Okay, so there's examples of angles that are not common, but it's pretty easy from my list up above to create pairs, either a sum or a difference, that would generate those angles. Typically, when you're picking a pair, you want to try to go with angles that are probably in quadrant 1 or 2. That should make the rest of your work just a little bit easier. It doesn't really make a difference. You could pick your pair from any quadrant, but 1 and 2 just makes it a little bit simpler. So for example, if I said give me a pair of angles that were 75, I probably would go 30 plus 45. Now by creating that sum, I can use 30 and 45 and use those numbers in the identity, expand it out, and I can evaluate using the unit circle. But 75 by itself, no, I would have needed a calculator to do that. Let's say we're doing 105, so let's do 150 minus 45. So this is what you need to do. You need to create a pair, and there are usually lots of options. So like, I could have come up with another pair that would give me 105. Like say I do 135 minus 30. Those things are all whatever you want to do, as long as it gives you the angle you're trying to evaluate. Any pair of any pair of common angles, should work. So like I said, I think with degrees it's pretty simple. I think when you go to radians, this should be simple depending on how you attack it. If you think of it as 5 pi over 12, how do I answer that question by using that set of angles, or how do I come up with a pair? I think you'll make it harder for yourself instead of doing like 12ths as a way to think about it. So here's the way I approach it. When I say 5 pi over 12, give me a sum or a difference. What I don't do is I don't in my head try to run from this list. Instead, what I do is I just say, think of any two numbers that would add to your numerator and be over 12, and both can reduce. If you can find that pair, you don't even care what those angles are to begin with. You can reduce them, and then you'll know what they are. So for example, if I want to get a 5, think of numbers that would produce 5 that are reducible over 12, fractions that would produce 5. So for example, if I said let's do 2 pi over 12 plus 3 pi over 12. Well, 2 over 12 reduces, 3 over 12 also reduces, and 2 plus 3 is 5. Now what I didn't need to know going in was that 2 over 12 was pi over 6 and 3 over 12 was pi over 4. So I didn't go, well, I guess it's pi over 6 plus pi over 4. I figured out the fractions that were 12ths that could reduce. That gave me a 5 as a numerator. And there are lots of possibilities. For example, what if I did, let's say 21 minus 16? Well, 21 over 12 reduces, 16 over 12 reduces. 21 minus 16 is 5. Now, when I reduce 21 over 12 and say it's 7 pi over 4, well, I didn't need to know that it was 7 pi over 4 going in. And 16 over 12, so 4 pi over 3. I didn't need to know it was 4 pi over 3 either. So I wasn't thinking about what they were as a over 3 over 6 over 4. I just had to get the numerator. Now, if you do that, creating a pair is pretty simple, and then you can reduce them and go, okay, here's what they are. So if it's me doing 5, I probably will do so 3 over 12 reduces, 2 over 12 reduces, and then yeah, I've got them in front of me so I can say, well, okay, 3 over 12 is really pi over 4, 2 over 12 is really pi over 6. So pi over 4, pi over 6 is what I would use to evaluate 5 pi over 12, but I didn't need to know that they were pi over 4 and pi over 6 in advance. Like pi over 12. Well, probably I could do the same pair, actually. There are tons and tons of options to do this. If you think about the 12s, I'm going to bring up the 12s list here. You'll find there are a lot of possibilities. If I wanted pi over 12, 16 minus 15, 21 minus 20, 9 minus 8, 15 minus 14, 10 minus 9, right? I mean, there's a ton of them. Now, usually I'm going to pick, like I said, stuff that's small as possible, quadrant 1 if I can. But lots of possibilities. If you want to get 13 or you want to get 23, same thing, right? I don't really need to know what pair from the blue list. I just want to get a pair from the green list. And then I'll reduce them and I'm good. So, for example, let's say I do 21 pi over 12 minus 2 pi over 12. If I don't need to know what 21 over 12 is. I'll reduce it and then I'll have what I want. Maybe I'll do an addition. Let's go 15 plus 8. Lots of ways to do it. So that's what you want to do. Just stay in 12ths, get your numerator, and you'll be fine. So when I go to do the actual problem, we'll do some of these in a second, then I would do 7 pi over 4 and pi over 6. But again, like I said, I didn't have to know that ahead of time. I just had to get the 23, and the two fractions had to be reducible over 12. Okay, hopefully that drives home the point on that. Let's get into some of the problems. So there's your unit circle. Again, thinking about common angles that would produce that, and that's what you're going to be using to evaluate. So there we go. Here's one of the reasons, one of many of the reasons that we did so much work with the unit circle in chapters 5 and 6, because it's going to keep coming back and help us with other problems. So here are your problems. Cosine of 75 or sine of 13 pi over 12. Basically, the first thing for you to do is create a pair. So if I'm doing the cosine of 75, probably I'm going to do cosine of 45 plus 30. As soon as I do that, what I've created is a cosine sum. So I'm going to use the cosine sum formula. All you've got to do at this point is lay it out with that formula, expand it out with the formula, and then go to your unit circle to finish the problem. So I expand it out with the 4530 using the identity. Then I go to the unit circle and replace all those with values from the unit circle and then clean it up. Square root of 6 minus the square root of 2 over 4. There's my answer. And a lot of the answers actually tend to look at the same because you are using your square root of 2 over 2, square root of 3 over 2 and a half, and probably most of the problems do your work. So you get a lot of these kind of typical root minus root over 4 kind of answers. Pretty simple to do. Just like I said, it's creating the pair. So let's say we did 13 and 12. So again, create a pair. So do you want to do a sum or a difference? And again, what I do is I think what plus what in twelfths will give me 13, but then both of them have to be reducible. So why don't you guys take a second to try to think of a pair, and then we'll... Okay, so hopefully you thought of a pair. Like I said, anything works as long as you get a sum of 13 or a difference of 13. I'm going to go with the sum. Tell you what, let's do, change the mind, let's do a difference. Now, I did pick things that were out of the first quadrant, but that's because 13 is pretty good size. I'm going to need something that's probably out of, beyond the second or first quadrant just to get my pair put together. But I chose 21 minus 8, which is 13. I do not need to know what 21 over 12 or 8 over 12 are going in. I just need to know that they'll reduce. Now I'll reduce them. So I guess I'm using 7 pi over 4 and 2 pi over 3. Didn't need to know that was what they were to start, but I got them now. Okay, so it's a sign difference. So I'm going to grab the sign difference formula and expand it out in the same way. Okay, so take a second to catch up. Now I'm just going to go through and run those values and see what I get. Sine of 7 pi over 4. Cosine 2 pi over 3. Cosine 7 pi over 4. Sine of 2 pi over 3. And again, you kind of said you get these sort of kind of standard looking answers. A lot of they'll be over 4, pretty typical because all your denominators are over 2, over 2, over 2. But that's basically it. I mean, that's how the formulas work. Very simple to use as long as you can find your pair. Okay, we're going to do a tangent, and then we're going to switch to kind of a couple other kinds of problems, and we're up the notes here and pretty soon. So the tangent formulas are pretty easy too. The only kind of major difference is that it's a fraction. The formula itself is a fraction. So it'll create a little bit more simplifying work. But outside of that, again, it's find your pair, plug it in, unit circle to evaluate, clean it up, whatever you get, you get. So let's say I decided to go 120 plus 45. Again, lots of options, plenty of things I could have chosen, but I'm just going to pick those two and then go ahead and expand it out. Okay, so again, just get it expanded out, go to unit circle, start filling in values. Okay, so let's fill our values, negative root 3, 1, negative root 3, and 1. Now, typically when I'm cleaning these up, usually I'll write it like this on purpose because if you think about stuff we've done in the past, this sets it up to rationalize the denominator and kind of has everything nice and neat. And that's the one catch with tangents is oftentimes you're going to have to rationalize the denominator. So we're going to go ahead and go through that, multiply by 1 minus root 3